Good morning, grade 12s. It is so nice to be with you guys today. I am Mrs. Ingrid Eckstein, and I will be teaching physics today. And then the topic that we are going to look at today is going to be electrodynamics. Now, when we look at electrodynamics, we actually already started with the build up towards here. So there's a lot of things that we are going to use from grade 10 and from grade 11 as well. And then especially with regards to electricity. We are going to look at our current, we are going to look at voltage, resistance, and then the power. And then if we look at electrodynamics, then electrodynamics is the study of the relationship between electricity, magnetism, and the mechanical phenomena. Now, those are the three things that I want you guys to remember today. Is we are specifically going to look at our electricity, then we are going to look at our magnetism, and we are also going to look at our mechanical phenomena. Now, our mechanical phenomena, that is now our mechanical energy that we are going to add, so meaning for rotation to take place, and then for motors to work, and then how generators work as well. Now, especially today with electrodynamics, we are going to look at electrical generators, which are used to generate electricity. And then we are also going to look at electrical motors, which are used for the powering and the operation of the machines that we work with in our houses and all of the appliances that we work with. So let's get started. So if we look at motors, then electric motors, now a very important question that they usually ask is, what is the energy conversion of an electric motor? Now you will see, if you look at the electric motor, that you are going to have a power source. So can you see here, if we look at the battery, that is then now going to be our power source. And then remember the three things that I mentioned earlier that I said you guys have to remember, and that is going to be your magnetism. So can you see the magnets with the north and the south pole? And then I also said we have to look at our electricity. And then we're also going to look at the movement. So that is now, you see the coil, that is where our mechanics is going to come in. Now, if we look at our motor, then you will see then, so here we have the coil that is going to rotate in circular motion. Then if we look at the battery, here we have the battery, north and then the south. Then we have the armature, and then also later on we're going to look at our carbon brushes. Let me just quickly make this smaller. Okay, thank you. Okay, so then we're also going to have our carbon brushes here, there, and we are also going to have our slip ring and split ring as well. And then, like I said, here we have our coil, and then the coil is then going to rotate. Now, if we look at our motor, then our motor specifically is then going to convert our electrical energy into mechanical energy. So it consists of a current carrying armature, which is then connected to a power source and by a commutator. So the commutator is then going to be your coil and the circuit that we work with. And then we're also going to have the brushes, like I said, which is placed in the magnet. Now, when we look at the motor effect, then we talk about the motor effect, which is the phenomenon by which a current carrying conductor is placed in the vicinity of a magnetic field. And then because of the magnetic field lines that you are then going to have between north and south, and then your coil that is within the magnetic field, that is then going to help the coil to rotate. And then also, because of the electricity that flows through the coil, that is then also why it's going to rotate then as well. So if we look at our magnetic field, so like I said, it experiences a magnetic force, your coil, which is perpendicular to the current, and the conductor and the magnetic field then, that is then what creates the rotation of your coil. And if we look at our motor, motor effect, then we are going to work with Fleming's right-hand rule for motors. Now, last year already, you guys learned about Fleming's right-hand rule, where you were supposed to work with a solenoid, and then your thumb has to show in the direction of your current, whereas then the coiling of your fingers shows the direction of the magnetic field lines. Now, this year, we are going to look at Fleming's left-hand rule for motors. And as you can see, you take your thumb, your index finger, and then your middle finger as well, and you put them at right angles to one another. So when you put them at right angles to one another, you will see then that here you are going to have the force. Then your index finger is going to show the magnetic field, and then your current is then going to be shown by your middle finger. Now, what they are going to do is they might give you, for example, the magnetic field, and they might give you the direction of the current. Then you have to be able to identify what is the direction of the coil. So is it then going to rotate in the clockwise, or is it then going to rotate anti-clockwise? So if we look at all the middle finger and then what everything stands for, then you will see here, so the left-hand rule is used to predict the direction of the movement of the coil in the motor. Then you point your index finger, so you point your index finger then in the direction of the magnetic field. Now remember, we always, or the magnetic field is always going to point from north to south. So your index finger, the one that you point everyone with, that finger, you are going to point then in the direction of south, so that you know that the beginning of your index finger, that is going to be north, and then the tip, so there where your nail is, that is then going to, so this is then going to be north, and then this is going to show to south. So then if I look at my middle finger, you point your middle finger in the direction of the conventional current. Now remember, if we talk about conventional current, then conventional current is always going to be from positive to negative. So that is now what we work with when we work with electricity. Then if I look at my thumb is then going to show me what is the direction that the coil is going to flip. So is it then going to flip upwards, or is it then going to flip downwards? So, or then clockwise or anti-clockwise. Now, when we will, later on, I will also show you that if we look at our pictures that they are going to give us, I will show you how you are going to flip your hands in order to get to the correct direction. Now, I want you guys quickly to take your left hand side, your left hand, and then I want you guys to make them at right angles to one another, like I showed you here with this illustration. And then your thumb is going to point upwards. Then you have your index finger, and then you are also going to have your middle finger as well. So can you see all of them are at right angles to one another? So there your thumb must be at a right angle to your index finger, and then you are going to open your middle finger so that your middle finger shows towards you. Okay, so then you can take your, so as you have your hand in front of you, you are then going to look at each one of the components. So remember, if we look at our hand just quickly again, then this force, this is now where your movement is going to come in. So remember the three things we mentioned in the beginning. So your thumb is going to show the movement. Your index finger is going to show the magnetic field. And then, so that is where you have your magnetic field. And then if we look at the current, your index finger is then going to show the direction of the current. And that is where we are going to have our electricity. Okay, so let's quickly look at the next slide, and then we look at how to identify. So with this one, I want you guys to identify in which direction is the force at AB. Now, when you look at a question like this, then I want you to, so can you guys see that the coil is split in two parts, né? Now, don't look at the coil as a whole. I want you to either, you are going to look either at one side, so CD, or you are going to look at the side at AB. If you are going to look at the whole coil, then it's going to confuse you. So you only look at one side. So remember the question, in which direction is the force at AB? So I want to know, is this coil, is AB going to flip upwards, or then is it going to flip downwards? And then obviously just the opposite is going to take place by C and then by D. So take your finger. Remember, we're working with our left hand, and then you take your finger and point it from north to south. So meaning your tip of your finger should point from north to south. And then you will see that we have our current. So if I look at my current, then my middle finger is then going to show away from me. And then you will see that your thumb is going to show upwards, which means that AB is going to move upwards. So your AB is going to flow upwards, and then you will see also that if we look at CD, CD is then going to flip downwards. So meaning in this case, it is then going to rotate clockwise. So you will either have to say in which direction A and B is going to move, or C or D, or then they will ask you, is it then going to flip clockwise or is it going to rotate anti-clockwise? Now, when we look at our motor effect, you will see that, so remember, we have electricity. So if we look at our energy conversion, remember our energy conversion was we plug something in, which means that we're starting with electricity, and then we are going to convert it into mechanical energy. Okay, so that is our energy conversion, which means in all electrical appliances that we have in our homes, we have more or less something like this in each and every motor. So we are going to have a magnet in a motor. Then we also have a coil in our motor, and then we're also going to have a power source. So there we have our power source. That is then going to be our electricity. And then because the electricity flows, so here we have our electricity. Because of our electricity that flows through the coil, that is, and in the vicinity of a magnetic field, that is then going to help the coil to flip into certain directions. Now, ladies, I don't know if you know, but the gentlemen, you guys will know, if we look at drills, then you have a drill, so you can drill something into a wall, and then you can also drill something out of, or you can take a screw or something out of the wall as well. So when we look at that drill is also going to be powered by a battery like this, and then it also has magnets in that drill as well. So there's a button that you can switch, and then you switch the currents. So then if I switch these currents, then it is going to rotate in one direction, and when I switch it to the other direction, then it is going to drill into the different direction. So meaning it can either go clockwise or it can then go anti-clockwise. Now, if we look at a motor, then the only type of motor that we are going to look at is we are going to look at direct current motor. Now, we have alternating current, so I'm sure you guys have seen already the signs AC and then DC. So AC stands for alternating current, and then DC stands for direct current. Now, if we look at the illustration that I have here, that is then going to be a direct current motor. Now, the way we know this is because of these components in the circuit that we have. So this component here is called a carbon brush. So a carbon brush, the function, we are going to learn more about that with the generators. But if we look at a carbon brush, then the carbon brush is going to be the reason why you have a completed, so I just want to right there. So you are going to have a carbon brush, and then that is going to be the reason why the circuit is then completed. So that completes the circuit. Then if I look at this ring that I have here, then this ring that I have here is called a split ring. So you will see when we start with the generators, we are going to have two different rings, but this one specifically is going to be a split ring. And that helps that your electrical current will flow in one direction the whole time in your coil. So on the, I want to say, the external part of your circuit, that is then going to be your coil. And this ring here, your split ring, that is going to be then the reason, or the function for that is for the current to flow in one direction the whole time. And that is then why we have a direct motor. Now, just the easy way to remember that, so think of, so we have DC, which means that that is then direct current. So unfortunately, if someone gets divorced, what do? They split up. So then you can remember that by looking at or just using this, and then D stands for divorce. So then you know a direct current will always have a split ring in the as a component for the electricity to flow. Now you will see these openings that you have here, so that is why we call it a split ring. That is going to be the reason that it helps the current to flow in one direction the whole time. Okay, people, so any questions regarding the motor? Then I'm going to carry on with the generator. If there's any questions, you guys are welcome to ask questions with regards to the motor, or you can just give me a shout if I can go on. Okay, so let's carry on with our generator. Now, when we look at our generator, then we have to go back to grade 11 work where we started or where we did Faraday's law. Now, can you remember if we looked at Faraday's law? Faraday's law was the law that we looked at in how it works to induce electricity. So Faraday, what he did is he took a current carrying conductor, and then he was busy with magnets as well, and there was a compass close to the current carrying conductor. So then he saw that if he looks at the needle of the compass, then as soon as he brings the current carrying conductor close to the compass, then the compass needle deflected. And then he realized that there's a connection between magnetic fields and electric fields. So if you can take electric field, then it influences the magnetic field as well. And that is how we got then to Faraday's law. So Faraday's law says the magnitude of the induced EMF across the ends of a conductor is directly proportional to the rate of change in the magnetic flux linkage with the conductor. So remember, if we look now at a generator, then a generator you do not have a power source. So there you have your magnetic field lines. So remember, your magnetic field lines flows like this. And then because of this conductor that we have, if we then turn it in the vicinity of a magnetic field, then we are going to induce electricity. So can you see now, once again, we are referring back to those three things that I mentioned earlier: electricity, movement, and then magnetism. So with the motor that we looked at, we had the electricity component, we also had the magnetic component, and then those two things then created that the force or the coil is going to move. If we look at a generator, we do not have a power source. So we have our magnets, there's our magnets, then we have a conductor, and then if we take this conductor without, now there's not any electricity yet, but we rotate this handle, then because we are rotating the conductor within your magnetic field line, that induces then a current. So you are then going to have a current that flows in your conductor. So therefore, that is then going to be Faraday's law. So just quickly read that again. You have to know that as well as a definition for this topic as well. So the magnitude of the induced EMF, so meaning we're going to induce an EMF across the ends of a conductor, is directly proportional to the rate of the change. Now that is where, so if we look at the rate of the change, then that is going to be where your coil is going to be rotated. And because of the coil that is rotated and it cuts with the magnetic field lines, that is then going to be your magnetic flux. That is then why an EMF is going to be induced. Now remember, if we look at our EMF, then remember Ohm's law says that if we look at a potential difference, then my potential difference in a conductor is directly proportional to the current if your resistance is constant, or if your temperature stays constant. So that is also something that we have to remember here with electrodynamics as well. Now, when we look at Faraday's law, then Faraday's law, this is going to be, if you guys remember, this is then going to be your EMF. Then this N that we have here, that is then going to be the number of turns or loops of the wire. Now, grade 12s, be very careful here when you need to explain something about the coil. Remember that you are not going to say we have a coil that we work with. You can't say that we are going to increase the number of coils. We usually say we increase the number of turns or the number of loops of the coil. If I say I increase the number of coils, then I'm actually saying that I'm adding another rotator like we have here. And that's not what we want to do. If you guys can remember what a solenoid looks like, then you will remember that you had a lot of turns on your solenoid. So please be careful when you speak about the turns or it's either the turns or the loops of the wire or in the coil. Then your EMF was directly proportional to the number of turns that you had in your wire. So if you have a solenoid or a coil with 100 loops and you have one with 50 loops or turns, then it means the one with 100 loops is going to create a greater EMF than, for example, the one with the lower amount of loops or turns. Then also, if we look at our magnetic field, so remember that is now the change, the rate or the change in magnetic flux linkage. Can you guys remember from last year how to calculate phi? So that was because of the strength of your magnet, it created then magnetic fields, and we measured that in Weber. And we calculated it by saying we take the strength of the magnet, that is then going to be in, that was in Tesla. And then we're also going to look at A. The A was then the area of the coil, and then cos theta. So that depended then on what the angle was between your magnet and your coil and how you move it. That is then going to influence what is the EMF that you are going to be induced. Now, whenever you see the words rate of change, then you know you have here at the bottom, you are then going to have delta T, so meaning the rate in change of something. So if I look at my Faraday's equation, then you can use Faraday's equation to then also say what are the things that we can change in order to induce a greater EMF. Okay, so if we look at that and we want to see then how are we going to induce a greater EMF, then we can say first of all, if I look at a greater EMF, so my first thing that I can do is I can increase the amount of turns in the coil. Then my second thing that I can do is, if we look at the change in magnetic flux, so there I can increase the strength of my magnet. And then, so remember here with the increasing of strength, remember you can't say I'm using a bigger or a smaller magnet. Please never say that. The reason for that is, I don't know if you guys also have a lot of magnets. That's usually where we put them, is on our fridge. You will sometimes see that you have small magnets and you have big magnets. But sometimes the smaller magnets are stronger than my bigger magnets. So please never refer to bigger magnets and smaller magnets. You're always going to say you're increasing the strength of my magnet, or I'm going to decrease my strength of my magnet. And then if I look at time, so now if you look at your equation, my EMF is directly proportional to the change in magnetic flux linkage. And then my EMF is inversely proportional to my time, so the rate at which it happens. Now, please remember, you can't say here, I'm decreasing the time. How am I going to decrease the time? So if I speed up my rotation, so I take this handle here and I rotate my handle faster. That is going to, so meaning I'm increasing the speed at which I'm rotating the coil. That is then how I am going to decrease my time. So please never say, I'm decreasing my time and therefore then my EMF is going to increase. I am decreasing my time. How? So therefore I am increasing. So I'm going to increase the speed of my rotations. Now, this is one of your topics in your question paper where you should get full marks. So you have only a few of your definitions that you have and that you have to study. And then the questions that they ask here are really questions that you can get a lot of marks. Now, usually a question like this will be about of electrodynamics is then going to be about 10 to 12 marks. And I want to see that you guys win with this topic. You can get 12 out of 12. So ensure that you know your definitions and that you then can identify the different or those three things, aspects of electrodynamics, and that you can then explain how each and every generator, motor, how they then work. So let's get started with our generators. So when we look at our generators, then the generator converts mechanical energy. So think about those three things that I mentioned earlier. So I've got my mechanical energy, then I have the electricity part, and then I also have my magnet. So my energy conversion here is going to be that a generator converts mechanical energy, and what are we creating? We are creating electrical energy. So then your mechanical energy comes from any mechanism that rotates. So this is now this handle here that is then going to be fastened to your coil, and we rotate that. So it rotates the rotor or the arm of the generator. And then when the turbine, so I will say more about this now, that is attached to the rotor. So usually this, when they induce electricity or create electricity, we are not going to have someone which are turning that rotor the whole time. We use a turbine. Now, we get different turbines. We get hydro turbines. We also have wind turbines as well. So hydro turbines and then wind turbines. We also have steam turbines as well. Now, think of here in South Africa, you guys know there by Garib, close to Eskom. So that is the movement of our water is then going to create this rotor to turn then, and that is what is going to induce our electricity. So when the turbine, which is attached to the rotor of the generator, turns, so that is your mechanical process. EMF, which is then your electrical energy, is going to be induced across the terminals of my generator. So can you see when you look at the picture that I showed here, then you have those three things. So you have your magnetic field, north to south. You also have your coil, and then within the coil, there you are going to have then your electricity, and then the movement of the coil, the one that rotates, that is where your movement comes in. Now, whenever you see this sign, that sign means that it is going to be an alternating current voltage. Now, if we look at our, when we look at our generator, then you can remember last year with Lenz's law, which states that the induced current flows in a direction so as to set up a change in magnetic flux. So you are not supposed to know Lenz's law. You can know of Lenz's law, but you didn't have to write it down. Same for this year as well. You don't have to write it down. You don't have to know, but Lenz's law, that is the reason why if we look at the magnet that we pushed into the solenoid, that is why there was a change in magnetic or the poles the whole time, because of the change in magnetic flux that it then induces. So the change in magnetic flux. So here we have our magnets from north to south. Then I have my coil. Can you see there I have my magnetic field lines? And then because of the conductor that then rotates within the magnetic field, that creates then a magnetic flux, and that is what creates then your current to flow. Now, if we look at our generator, we are going to look at two types of generators. We are going to look at our alternating current generator. We are also going to look at our DC generator. Now, remember here, when I explained with the motor, this is now also where those two rings come in as well. So we have our, remember with the motor, we said then that is going to be our direct current motor, but now this is just going to be generator. So we work with our DC generator. And can you guys remember the two types of rings that we have? We have a split ring, and then we also, the other one is then going to have, we have a slip ring. Now, the split ring, can you remember if people get divorced, then they split up. So therefore, then that is going to be a split ring that we use with a direct current. And then if we look at the alternating current, that is then where we are going to work with the slip ring. So your split ring goes with your direct current, and then your slip ring goes with your alternating current. Now, let's quickly have a look here. So this is a representation of an alternating current. Now, with your alternating current, that is where you're going to get most of your questions, because this is where we can have a lot of calculations as well. Now, let's quickly look at every part of our AC generator. So when we look at our AC generator, we have our armature. So our armature is the coil that we look at, that we have on our external circuit, and that allows EMF and current to be induced as it rotates in the magnetic field. Then we also have our magnets. So our magnets, that is then going to help to create a magnetic field. So and that is why also, so we are taking the armature, we are moving it in the vicinity of a magnetic field, and that creates your electricity. And then with this one specifically, because we are working with the AC generator, we have slip rings. Now, the slip rings allows the current to change direction every half revolution or half rotation of the armature, and then it also allows contact with the brushes so that the current can be transmitted to terminals without breaking the circuit. So can you see here at this point here, that is where it comes in contact with your brushes. And then because it is in contact with your brushes, we can also then create electricity to flow through your external part. And then if we look at our carbon brushes, so our carbon brushes, they can also ask you what are the functions of the carbon brushes. So these small cubes that you see there, that is then going to be your carbon brush. Now, your carbon brush are there specifically to complete the circuit. So you will see there you have, it maintains electrical contact with the slip rings. So that is to complete the circuit. And then you also, it conducts or takes current out of the coil. So can you see the one on the one side, it's connected to a slip ring and a carbon brush, and then on the other side. So specifically functions for my carbon brushes, it completes the circuit, so maintains electrical contact with the slip ring, and then also it conducts or takes the current out of the coil as well. Now, grade 12s, these are important things or components that you have to know in order that if they ask you for the functions of each one of them, that you are able to write down which or what is the functions for each one of the components. Now, if we look at a direct current, just quickly before I go on with the direct current, our alternating current. So I haven't spoken now about your slip rings. So when we look at our slip rings, can you see that they are circular rings? There's no gaps within them. And the reason we use the slip rings is because we are busy now with our alternating current. So that is then going to help that if this coil rotates the whole time, the current is going to alternate every single time. So meaning if I look at this coil, as it rotates, then when it gets to a different point, then all of a sudden, instead of the current here flowing downwards, now your current is going to flow upwards. And here where your current was flowing upwards, now your current is going to flow downwards. So that is why we have these slip rings, and that is so that we can initiate the alternating of our current. Now, when we look at our direct current is then going to, so remember DC, D, divorce, split up. So can you see if we look at our ring, then there's splits in the, or openings in the rings. And that is to help the current to go in one, or to flow in one direction the whole time. Now, can you see all of the components are still the same? So if we look at our basic components, we have our armature. The armature allows the EMF and the current to be induced through it as it rotates in the magnetic fields. Then we also have our magnets. The magnets provides the magnetic field, and this is now where the stronger our magnets are going to be, that also means then the stronger our magnetic field will be as well. Then we have our split rings, or split ring commutator. We can talk about that as well. That is now, like I said, helps for the current to flow only in one direction. It also allows continuous contact with the brushes so that the current can be transmitted to terminals without breaking the circuit. So here, can you see that your slip rings are connected to your carbon brushes as well? Now, your carbon brushes, they are made out of carbon or then we also have graphite as well. But graphite is just it also consists of carbon as well. That is just a different way of naming them because of the way that they react with one another. If you guys can remember from grade 11 and grade 10, you had different allotropes of carbon, and that is the way that they react with one another. They have different functions. So graphite can conduct electricity. Then if we look at our carbon brushes, it maintains electrical contact, so meaning it completes the circuit, and then also it takes the current or conducts the current out of the coil. Now, grade 12s, it's important for you to be able to identify each of these components, and then you have to be able to give their functions as well. So for 1 or 2 marks, and these are easy 1 or 2 marks that you can get. So you should score when it gets to electrodynamics. Now, when we look at the generator, then we're also going to work with the Fleming's right-hand rule. So now you guys have to remember that we have the motor. The motor works with the left hand. Now think about how we drive. So if we drive in the road, then we drive on the left-hand side. So therefore, my motor, you are going to use your left hand, and then with a generator, you are going to work with your right hand. Now, the way that I usually remember that is with the driving on the left-hand side. And then if I look at the word right, so G, generator, and then right hand, both of them has a G in it. So therefore, then I remember generator works with my right hand, and then the motor is going to work with my left-hand side. So if I look at the 3 things that we've mentioned earlier, the 3 main things you will need to focus on is the force, the magnetic field, as well as the current that is going to be induced. Now you are going to take your hand exactly the same way that we did with the left-hand side as well. You are going to take your right hand, you are going to point your thumb upwards, you are going to take your magnetic field, or so your index finger, point that straight as if when you were little and you're pointing it to someone that you are going to shoot. And then you take your middle finger and you put it at a right angle to your index finger. So you will see here also, you can remember the acronym FBI. So F, where do we work with F? That is with Newton's laws. When we work with F, that was the force, so meaning in which direction is it going to rotate. Then we have our magnetic field. That is then going to be B. So remember the equation that I showed you guys earlier, where we had BA cos theta. So then this B is then going to be the direction of your magnetic field. And then you also have your current. So your current, it has to, then your middle finger has to show in the direction of your current. Now, if we look at, you need to be able to discuss this as well. So using your right hand, point your thumb in the direction of the force. The index finger must point in the direction of the magnetic field, and that will always be from north to south. And then your middle finger will point in the direction of the current. Now, also remember from last year that there's another way of showing how current is flowing. So they did this, and then in the one circle, they had the crosses, and then in the other circle, they had a dot. So here where you have the cross, now think of a dart, né? So if you take a dart, when you're playing darts, then if you throw the darts away from you, you see the plier, that cross at the back. So meaning then you know that the current flows away from you. But if the dot is coming towards you, you are going to see the dot. So the tip of that sharp point is going to come towards you, which means then that the current is going to flow towards you. So out of the paper, this is going to be out of the paper. This is going to flow into the paper. So remember that they can show it to you guys in that way as well. So let's quickly look at how to use then your hands in order to identify in which direction your coil will flip. So in this case, since the armature is rotating clockwise, part AB moves upwards whilst part CD moves downwards. So the direction of the force is going to be upwards. Now quickly take your right hand, put it at right angles to one another, and see if you can then identify with your hands that it indeed flows upwards. So your first thing that you are going to do is start with your index finger. So point your index finger in the direction from north to south, and then you take your middle finger, because the force is the thing, the component that we want to look at lastly. Then your index finger is going to point in the direction of your current. Now remember what I said, we only look at one side at a time. You are not going to look at the whole coil. So then your index finger, north to south, your middle finger, can you see that is then going to flow away from you? And therefore then can you see that your thumb then shows upwards, which means that AB is going to flip upwards, and then BC or CD is then going to flip downwards, which means then that if you have to say clockwise or anti-clockwise, it means in this case, it is going to rotate clockwise. I know this feels strange, but remember, each one of you, when you do these things and you're writing exam, you guys are not even looking at one another. So grade 12s, it might be funny now to sit with your hands and to identify in which direction the current or the force is going to be. But remember, you are responsible for your marks. So take out your hands and put your fingers at right angles to one another, and then you identify what is the direction of your current or the direction of your force then going to be as well. Now, if we look at our generators, so can you see here, I have then my magnetic field. So remember, we're always going to show from north to south. And then if we look at the current. So here in this one, how do we determine the direction of the current? So now you have to, your middle finger is the last thing that you are going to open. So your first thing or finger that you are going to use, you always use your index finger first. So from north to south, so point it north to south. Then you know that this side of the coil is flipping upwards. So you point your thumb then upwards, and then if you open your middle finger and you put it at right angle to your index finger, then you will see that it points away from you, which means then that your current is then going to flow upwards. Go and practice these things. So take your books and your booklets, revision booklets as well, and go and practice. Look at each of your pictures that you see and go and practice what you, the direction of your current or the direction of your force, and then go and look at your direction of your magnetic field then as well. Now, if we look at our alternating current, then or alternating generator, this is now where we are going to work with our graphs as well. Now, because it rotates 360 degrees, you will see that if we look at alternating current, it creates a maximum voltage and it creates a minimum voltage. Now, if you can remember from last year, you had a galvanometer. That galvanometer had a needle. So that needle will either, if you push in the magnet to the solenoid, it's either going to deflect to the one side or it is then going to deflect to the other side. So if you push the magnet into the solenoid, then it would deflect to the right side. If you pull it out, then it's going to deflect to the left side. Now, if we represent that on a graph, then this is how we would represent, for example, current over time on the graph. So you have alternating current, which means that it creates a maximum current. Then when your needle goes back to zero, here you have then it goes back to zero. And then when it goes to the other side, you are then going to have a minimum. So you are always, when you look at your graphs with the alternating current, you are always going to have that it goes to the maximum and that it also goes to the minimum. Then we have our voltage versus time graph. So voltage versus time graph, there you have exactly the same. You have then where your voltage is then going to move to the, or you're creating a maximum voltage and also your minimum voltage as well. So can you see here, if we look at the current and the voltage, remember I spoke about Ohm's law earlier. So your V, or potential difference, is directly proportional to your current, and therefore the shape of the graphs also look the same as well. Now, can you guys remember from grade 10 that we worked with our frequency as well? So when you look at the graph, you had one wavelength, né? So one wavelength represents then one oscillation or one rotation of your coil. And then so up until here, you had half of a wavelength, and then your wavelength then goes from the start to the end. Now, this can give you, this is about when they ask questions like this to draw the graphs. You don't have to draw them usually according to scale. You have your voltage over time and your current over time, and then you just have to look at where the coil is at so that you can then know where to start. And then they will tell you there was 2 rotations or it was only 1 rotation. So if it was 2 rotations, you would have just carried on and created then another graph as well, so that you can then or show that there was then going to be your 2 rotations. Now, if we look at our waves, then remember your waves, you still have all of your properties as well. So remember you had frequency, and then you also had period as well. And then if you guys can remember how to calculate them, we had F equals to 1 over T, but then because frequency is inversely proportional to period, then T equals to 1 over F as well. So therefore, if I have the frequency, for example, then I can go and calculate my frequency. So then we see here that in South Africa, Eskom generators in the power plants produces alternating current that has a frequency of 50 hertz, which means then I can go and calculate what is my period going to be. Now remember, the definition for period was that it is the time that it takes for one wavelength to be completed. So meaning if I say then 1 over 50, that equals then to 0.02 seconds, which means that if I look at this voltage over time graph, then for this whole wavelength to be completed, it only took 0.02 seconds. So that is also type of calculations that you are supposed to do and that you have to remember from grade 10 as well. Now, when we look at how to draw them, then first of all, if you look at, you have to go and you have to look at what is the direction or what is the position of your coil going to be. So when you look at your position of your coil, the coil is in a vertical position at this time. So can you see here, it's upward, so it's in a vertical position. And then if you look at the black side of the coil, is at the bottom, whereas the orange side of the coil is at the top. The sides moves parallel to the magnetic field when moving past this position. And can you see that they don't cut with the field lines? So can you see there's your opening and the magnetic field lines goes through this opening, which means that the coils that you have, they don't cut with the magnetic field lines. So therefore, there's no change in magnetic flux, and therefore then your EMF and your current is going to be 0. So meaning if we look at that point here on the graph, then that point at the graph is then going to be 0. Now, as it rotates, you are going to see that your EMF is slowly then going to increase until it rotated 90 degrees. So there where it rotated 90 degrees, now the coil turns 90 degrees to a horizontal position, and the coil cuts perpendicular through the magnetic field lines when moving past this position. So at this position here, that is then the maximum rate of change in flux. So can you see these points of the coil, the orange side and your black side? Both of them are now, they're cutting with the magnetic field lines. So there's your magnetic field lines, and they're cutting the magnetic field lines, which means then that is going to create the maximum. Now, if we look at the graph, so can you see there where my coil was vertically, now it started turning, so it rotated 90 degrees, and now it is at its maximum EMF or then current. Then if it rotates another 90 degrees, then can you remember, now you will see that previously the orange was at the top and the black part of the coil was at the bottom. So now it actually rotated 180 degrees. So therefore, if we look at this, now our magnetic field lines goes through the opening, which means then there's no change in magnetic flux, and therefore my graph is then back to 0. Okay, so now my coil flipped or rotated 180 degrees. And then if we look at the next one, you are then going to rotate and it's going to be at its maximum. Okay, so if we look at this, then it is going to be at its maximum. And then you will see when it goes back to its original place, where your orange is at your top and the black part is at the bottom, that is then where it made a full rotation, which means that it rotated 360 degrees. So you guys have to be able to then identify, if you have to draw something like that, then you have to identify where are you going to start. Now, if we, for example, look at this part, at this one, then they can give you a picture like this, and then they will ask you, start the graph or give a graph of potential difference over time, and then they can ask you, but start for one rotation and start the graph at the position where the coil is at the moment. Now you will have to look at your position of your graph. You will see that at that point, it creates maximum voltage and maximum current. So then instead of starting by 0, you are going to start at the maximum point, and you are going to then form one rotation. So that was now part of grade 10 work that you guys had to draw the waves. So you're starting at the maximum, it goes down to the minimum. So up until here, it rotated 90 degrees. Then you have another 90 degrees, another 90 degrees, and then there it is back to where it started. So please ensure that when you practice your graphs, that you are able to draw the graphs from any position that your coil is at. So when it is at a maximum position or when it is at a minimum position, you need to be able then to draw all of them. Now, this is what also one oscillation would look like. So can you see here? This is then going to be your vertical. Then your coil is parallel with your magnetic field. That is going to be your maximum. Then again, you are going to have your vertical, where absolute no EMF is going to be induced. Then it is parallel with your magnetic field, which means that is again at a maximum, but now just in the other direction. And then when it is vertical again, you are then going to be again by 0. Now, those are also easy marks that you can get as well. Then grade 12s, we also have our DC generator. So our DC generator works with, can you see here, again, like the motor, what type of, who can tell me what type of ring do we have there? Is it a slip ring or is it a split ring? So can you guys remember? DC stands for divorce, so that is direct current. And what do people do when they get a divorce? They split up. So therefore, this is going to be a split ring commutator. Now, can you see if we look at our split ring, then there's gaps. And then as soon as those gaps are across from your brushes, then there's a gap in the circuit, which then helps the circuit to go in one direction in your coil the whole time. And that is one of the major differences when we look at our motor and when we look at our generator. So DC generator has a split ring, where your AC generator has a slip ring. So please, grade 12s, remember that, and then also remember the functions of them as well. Now, when we look at our DC generator, you can also use your right-hand rule in order to identify in which direction the coil is going to flip. So here you are going to also use your right hand, Fleming's right-hand rule. You point your index finger in the direction from north to south, and then if they told you in which direction your current is, so if you look at your current, now your current is not flowing. So if you look at this position here, then your current is not flowing away from you, but it is flowing towards you. Now, the only thing you do is you have this position in your wrist. I will show you guys later as well, where you can then just rotate your wrist and then show in which direction the current flows. And then you will see, if you got it right now, then your thumb shows downwards, which means then your AB part is going to rotate downwards, and then your CD part is going to rotate upwards. So meaning that is then going to be anti-clockwise. Ensure that you go and practice this. These are easy marks so that you can get to what direction, or in which direction is north and south. So where's north, where's south, in which direction is the current as well. So can you see then here you had your force then for AB part, that is then going to go downwards. Okay, now let's quickly look at our graph. So with a direct current, instead of your graph going to the maximum and the minimum, remember your current flows in one direction the whole time, which means then you are only going to be on the positive or then the negative side of your Cartesian plane. So this is then going to be where there's no EMF that's going to be induced. That is then going to be here. When your coil is parallel with your magnetic field, then it reaches the maximum. Then it rotates again, another 90 degrees, which gives you then a total of 180. And then it rotates again to 270, meaning it cuts with a magnetic field, so creating a maximum EMF or inducing maximum EMF. And then again, if you look at this part, your magnetic field lines are going through the opening of the coil, which means then that there's going to be no EMF induced. So please ensure that you are able to draw these graphs. If they, for example, give you a picture of a direct current and they start with the coil in this position, then remember you have to start at this point. And then just at the end, you are just going to add another part so that you know that you have one rotation. Go and practice this, grade 12s. It's easy marks, so that you can ensure that you get all your marks here. Now, if we look at the uses of a DC generator, then some of you might have started with electrochemical cells already. So this is a DC generated direct current. We use the batteries in factories for electroplating. So that is to cover a metal with another metal. Or also we use it in factories for electrolysis, and that is also to create electrons to flow from an electron flow from one element to another. And then also in locomotives where that's driven by a diesel electric motor, that is also then direct uses of the DC generators. Then if we look at our alternating current, then the advantage of a current that alternates is that it is easy because it goes from the maximum on the one side to the maximum on the other side. It is easy for an AC generator then to transfer your electricity from one point to another. Now, here by the power station, when electricity is induced, we start here with a voltage more or less of 22,000 volts. And then the ampere that we use, so that is extremely small, 0.5 ampere. Now remember, voltage is the amount of energy that is transferred per coulomb of charge. If I look at current, current equals then to the rate of change in, or rate of flow of then your charges. So now each one of these charges, they are filled up with 22,000 joules per 1 coulomb. So that's now again a little bit of electricity. So that means that we can then transfer a lot of these energy. We can transfer then from the power station to then our transformers. From the transformers to the industrial consumers. And then we also have our substations. So each municipality as well, where it is sent to. And then from the municipality, it is sent to the transformers that is in our different suburbs. And that transformers then, it decreases our voltage so that our households only are supplied with about 220 to 240 volts. And then they increase the ampere to about 50 ampere. So can you see from where we start to where we end, we say that they step down the voltage or they step up the voltage, same as with the current as well. They step it up or they step it down. And because they can step it down, that it means that we can then send this energy over a long distance without losing a lot of energy. And that is the advantage of an alternating current, is because we can step it up and then we can step it down as well. Then, so alternating current can be stepped down or stepped up. It can be transferred over long distances with minimal or no loss of power. And then also your AC current can be generated in much higher voltages than, for example, your DC. Now, grade 12s, because of the fact that we can generate it at a very high voltage, minimum and maximum, when we are supplied with a certain amount of current, then because we're using or we're getting alternating current to our homes, then we are working with something called root mean square. So here you will see RMS. Now, if we go and we look at our graphs, so these graphs that we had, especially with our alternating current, then with the alternating current, if we go and we look at the mean, so meaning the average, then if we take the average, we are going to get to 0 because our maximum is the same as our minimum. So then what they did was they got to a way that they can calculate the voltage and also our current, the output of that, and that is what we call our root mean square. So our root mean square definition says it is the root mean square potential difference. So here we have that is the AC potential difference, which dissipates the same amount of energy as an equivalent DC potential difference. So that means that if we look here at our alternating circuit and the DC circuit, if we had exactly the same voltage, then and we had the same power in the AC circuit, and we had the same components as well in my DC circuit, then this circuit here with the alternating current is going to give us more or less the same voltage, the same output as then your DC generator going to give us. But like I said, there's much more or many advantages to an AC current than, for example, a DC current. DC current, you can't change it. But with the AC current and voltage, you can step it up and you can step it down. Now, you will see if you go and look at a lot of, all of us have cell phones, and then you will see that you plug it in, you have that box there by the electricity where you have to plug it in. Now, if you look at that, then that is a transformer. So that transformer can increase your voltage or it can decrease your voltage, but specifically your ampere. So you will see then that it gives you a certain ampere to charge your phone with. Now, if we look at our root mean square current, our root mean square current is the alternating current which dissipates or produces the same amount of energy as an equivalent direct current. Okay, so if we look at our RMS potential difference and current, then our households currents are then and voltages are then RMS. We use small letters with that, and then we use that for subscripts as well. And this is very important. So when you guys do your calculations, then your calculations has to have so can you see here, VRMS, you also have your Vmax, you have your IRMS, and you also have your Imax then as well. So since AC varies sinusoidally, you will see, so it's sinus waves or sine waves with as much positive and negative. Doing a straight average would get you 0 for the average. So that is why we work with the root mean square. Now, if we look at our root mean square calculations, then this is the equation. We are going to get, for example, maybe the maximum, and we need to calculate what is the root mean square. Same with this one as well. You have a VRMS as well as my Vmax as well, divided by my square root. Okay. Now, if we look at my calculations, then the calculations that we have, so when we look at our information sheet, we can use the information sheet from our electric circuits, as well as with our, so can you see here specifically, that is going to be our alternating current. So therefore, we then have our VRMS that our household implements are using, as well as my IRMS as well. Now remember, we also work with our power as well. So this is like an average. So remember, it's your root mean square. Means it's your average. So therefore, if we look at the power calculations, then we are also going to work with our average power as well. If you forget that average, grade 12s, then you forfeit your marks. So please ensure that when you calculate or do the calculations, that you add your average as well as your VRMS and then your IRMS as well. Your current stays the same. But can you see there where you use your, there where you have to calculate your potential difference or your current, you have to add what are you working with. We are going to work with our VRMS and then also our IRMS as well. Now, let's quickly look at an example. So before our time runs out, and then you guys can go and practice it yourself as well. Now, if you look just before I carry on, you will see that you have Ohm's law as well, né? So you have R equals to V over I. Now, when you work with that equation, you also have to use it and use your subscripts for alternating current. So remember, we are working now with our VRMS. So you have VRMS as well as your IRMS. Please ensure that when you use that with alternating current, you have to write there your VRMS as well as your IRMS as well. We are quite strict on that at the end of the year when with the marking. So use your subscripts so that we can see exactly what you are calculating. Now, our first example question is, first of all, they're going to give you an illustration like this. Now, if you look at your illustration, you will see that you have symbols P and then Q. You need to know what each one is. So if we look at P, then those small boxes is again your carbon. So that is then going to be your carbon brushes. Then if I look at Q, Q is then going to be a ring. But then which ring is it going to be? Can you see that the ring is split, so there's gaps in between. So therefore, that is then going to be a split ring commutator, okay? And can you see that if we look at this illustration, that there's no power source. So because there's no power source, we know that this is going to be a generator. Now, luckily, in your first question, they give you that. So they tell you which components, P or Q, enables this generator to produce DC current. And that is then going to be your split ring commutator. So your split ring enables this generator that it is then going to be a direct current. And now look at your second question. They ask, what structural change must be made to this generator to change it to an AC generator? So remember now, split ring and slip ring. So this is a direct current, and we want to change it now to an AC generator, which means that we have to take this split ring and we have to replace it with a slip ring. And that then enables your generator to then go to a AC generator. So can you see grade 12s, the type of questions that we then get in this topic? Very easy, and all of you are able to get to all of your marks when we look at electrodynamics. Then if we look at the next one, so they say, briefly explain why Eskom prefers using AC instead of DC for long distance transmission of electricity. Now remember, I said to you, if you look at the advantages, then because it has to be transferred over long distance, then we can step it up and step it down, which means then there's not going to be a lot of power that is lost. So AC can be transmitted over long distances with minimal or no loss of power. And can you see grade 12s, you get 2 marks for that. So ensure that you mention everything, rather write too much than too little. So then you mention, if it's for 2 marks, mention what you know, what are the advantages, so that you can ensure that you get to all of your marks. Then by question 10.4, so look now at what they give you. They say an AC generator delivers 240 RMS to a 60-watt light bulb. The peak current in the light bulb is 0.35 ampere. Okay, so then they ask, calculate the RMS current in the light bulb. So now remember, they ask, or they said here, the peak current in the light bulb is going to be 0.35. So they ask now, so calculate your RMS current. Now remember, if we look at our equations, then at your formula sheet, then in order to calculate your IRMS, you are going to use this equation. So IRMS equals to I max divided then by your square root of 2. So therefore then, if you look and you calculate then with your, let me just quickly go. So there, if you then look at your RMS current, then you substitute, so ensure that your formula is correct. You have IRMS equals to I max over then your square root of 2, and then you have 0.35 divided then by square root of 2, which means that your IRMS, that is then going to be 0.25. And then in your next question, you will see that they ask, calculate the resistance of the light bulb. So your resistance of the light bulb, now you have to go and look at your different equations. So if you look at your different equations, you can have also, you have R equals to V RMS over I RMS. And then you also have P equals to I RMS times V RMS. P average equals to I RMS squared, or P average equals to V RMS squared divided by R. Now, if you look at what you have given or what you were given, which equation are you going to use? So I have now 240, so I have my V RMS. Then I also have my power, my wattage as well, And then in our previous question, we also calculated our IRMS, which equaled then to 0.25 ampere, which means that we have a lot of information in order to calculate our resistance. Now, usually with these type of questions, there's a few ways that you can get to the answers. So as long as you use the correct formula, you substitute correctly, then you can get to your answers and you can get your marks. So then to calculate our resistance in the light bulb, we then have P average equals to VRMS squared divided by resistance. And then to calculate my resistance, then you have 960 ohms. Now, the safe thing to do here was to use your 240 RMS in order to calculate your resistance. So you have to go and look for an equation. So you can either use this one or you can use this one, because for both of them, you have a resistance in them. But remember, with 10.4.1, you had to calculate your RMS current. So let's say you made a mistake there, and now you're carrying on with that mistake further on. Then it could cost you some marks. But luckily, we do apply positive marking. But it is always safe when we calculate and we have formulas that we use the formula so that we can use the information that was given. So that is then the safest one to use then here is your P average equals then to your VRMS squared divided then by R. Then grade 12s, let's quickly look at another one. So with example, or I see it carries on. So how many rotations are made by the coil in 0.03 seconds? So this is now where we apply our graphs. Now, if I look at 0.03 seconds, so there, what is the amount of rotations that we have? Now look at your graph. It goes to the top, then it goes to the bottom, and then it goes to 0 as well. So there we have one rotation. And then from 0.2 to 0.3, we are then going to have a half of a rotation, which means that the total amount of rotations is then going to be 1.5. Then if we look at, so when we look at 10.5, so 10.5, so you see here 1.5 rotation. If we look then at 10.5, so calculate the frequency of the alternating current. So now remember, we had frequency equals to 1 over period of period equals to 1 over frequency. Now we want to calculate our frequency and then also look at what the numbers that you have. Now, previous question, they asked that on purpose so that you can see that this is 1.5 rotations. When we calculate our frequency and we have to use period, then we have to use only one rotation or one wavelength, because period's definition says that is the time that it takes for one oscillation or one rotation or one wavelength to be completed. And then my time that I'm going to use is going to be 0.02, not 0.03, because we have to use only the time that it takes for one oscillation or one rotation to be completed. So therefore, we are then going to say frequency equals to 1 over period, and then 1 divided by 0.02, and that gives me then 50 hertz. Then by 10.6, so by 10.6 they say, will the plane of the coil be perpendicular to or parallel to the magnetic field at time 0.015 seconds? Now, if we look at 0.015 seconds, so that is then going to be at this point, which means it is going to be at its maximum. So this is now where you have to identify what is the position of your coil then going to be. And your coil in this case, so remember that is where it cuts. If you look at your coil at this point, your coil is going to then cut with your magnetic field lines, which means then that that is going to be parallel to. Then by 10.7, they ask if the generator produces a maximum potential difference of 311 volts. Calculate the average power. So now you will have to go and look at what do you have. Now analyze your question. So can you see, if you look at your graph, you have your I max, né? So you've got your I max, and go and make like I usually tell my kids they have to go and make a list. So go and make an inventory list of what you have. You have your I max, that equals then to 21,21 ampere. Then they also say we have a maximum potential difference. So that means my V max is then going to be equal to 311 volts. But can you see that they ask for power output? Okay. Now, when we look at our power output, I can calculate my power by using either, I don't think we have this equation on the information sheet, grade 12s. Please don't use this one. We stick with these ones. So P average equals to I RMS times V RMS. P average equals to I RMS squared times R. Now you will see that we do not have resistance. So rather than don't use one that we have resistance with, we have then I RMS and then also V RMS. So my first step is I will have to go and calculate what is my I RMS, what is my V RMS. So then I know my I RMS equals then to my I max over then my square root. So quickly take your calculators and then you calculate that. Your I max is going to be 21,21 divided then by your square root, which is then going to give you equals then to 14,99 ampere. Okay, and then if we look, remember always to round off to your second decimal. Then if we look at our V max, so I want to calculate my V RMS. So my V RMS, we've got V max divided then by my square root. That equals then to, they said we have 311 divided then by my square root of 2. So go and calculate that. And that gives you then 219,91 volts. and then you can go and calculate your power. So then P average equals then to your IRMS times then your VRMS, and you substitute what you got there. So my IRMS was then 14,99, and then your VRMS, that is 219,91 volts. And if you multiply those with one another, then you get to 3,296,45. And remember, we have then watts. Okay, so can you see here, if we look at the mark allocation, my mark allocation is then going to be 5. So usually if we have a mark allocation of 5, we know then that it is going to be multiple steps. So therefore you have to show all of your multiple steps so that you can then also get to your answer. Okay, let me quickly, so can you see there, they just used a different way in calculating, so they used that top equation that I said to you guys, we don't get this one on the information sheet, so therefore rather don't use it. If it is there, you can use it, but remember we always use the information that is on your information sheet, and we get to more or less the same answer. Okay, grade 12s, then also just to check quickly and identify what is the direction of your current. So if we look at this, then we are going to have a generator because there's no power source. So they say a part of a simplified DC motor is shown in the sketch. And then they ask in which direction, A to B or B to A, is the current flowing through the coil if the coil rotates anti-clockwise as indicated in the diagram. Now you know that this is then a motor, where I see here, can you see that? That's why they say only a part. So they did not give you or tell you whether there's a galvanometer or then also a power source, because they said that. So you have a DC motor, so you have to know there is going to be a power source. And then can you guys remember with which hand you have to work with when we work with a DC motor? So your motor is then going to be your left hand. So grade 12, take your left hand, then you point your fingers in the directions. So first of all, I said now your left hand. So you take your left hand, you point in the direction from north to south, and then if you look at the
Excuse me,
rotation.
excuse me.
Yes, yes. You can speak.
This is Albert Mahoka. We have a question here.
Yes, you are welcome.
Are we allowed to ask the question?
Yes, please, you can ask.
All right.
Ma'am, so I just want to confirm one thing first. For the external circuit of an AC generator or an AC machine, is the current also alternating in the external circuit?
Yes, that is correct.
Okay, so let's say we're doing calculations with an AC current. How do we assume the direction of the current, just like with your normal electric circuits, if the current is alternating?
So that is something that you will have to go and identify by using your hands. So if you look at your alternating current, they will specifically give you a picture. I'm just quickly going back so we can look at a picture. So they will specifically give you a picture at a specific moment. So then you can, at that specific moment, you have to then be able to identify what is the direction of the current at that specific moment, because your current is alternating the whole time. So they can't ask you while it rotates, what is the current, the direction of the current. So they have to stop it at some point and then ask you at that moment, what is the direction of the current. Does that answer your question?
Thank you, ma'am. Yes, ma'am. Thank you.
Any other
Thank you.
questions?
No, we are good.
Please just mute yourself, please. Okay, grade 12. So if we look then at this picture, so now you take your, like we said, you take your left hand and then you point your finger in the direction, your index finger, north to south, and then you will see that this side of the coil is going to flip downwards. This side of the coil is going to flip upwards. Now, we're only going to look at one side. Otherwise, you get confused. Now, if you look at that one side, then your index finger points from north to south, and then if you take your wrist, then you flip your wrist so that your thumb goes downwards, and then you will see that your middle finger shows away from you, which means then that your current flows up in that part of the coil, which means that at this moment it's going to flow up in that direction, down in this direction, which means then that your current is going to flow from A to B, and in the picture at that moment where that they showed you there. So then they ask by 1.1.2, name the rule you use to answer question 1.1.1. And then if you remember grade 12s, you can somewhere say that. So that is going to be Fleming's left hand rule. So please remember, you have your left hand and your right hand. So you have Fleming's left hand rule, and that is then what you use in order to then identify in which direction the current is going to flow. So that is because of time that we are done then for today. Please take a picture of this question, and then you go and you calculate this question, and then we can also, you have the revision booklets as well. Please go and use the revision booklets to practice exam type questions then as well. Okay, grade 12, all of the best. Go and study this topic and ensure that you can get all of your marks here. All of the best.